Alright guys, we are going to delve into the world that is stoichiometry. This is sort of the crux of high school chemistry, right? But an important topic to help prepare you for down the road. If you happen to take a general chemistry class in college, which you might have to do for a variety of reasons, right? You're going to be glad that Ms. Huberberg took the time to make you suffer through stoichiometry. All right, moving on. So stoichiometry is the calculation of the theoretical yield in a reaction when you have known quantities. So to put that in better terms for you, right? Why would we care what the theoretical yield is? So we're talking about how much of something are we going to make in a reaction, right? Now that's important. So when we go into the practical uses of chemistry, so not just like in a lab where I ask you to mix this much of this with this much of that, right? And then we get something of something, right? Why is it important for just a typical chemistry student to understand how to calculate how much we're going to produce of something? Well, that typical high school chemistry student might someday be like a pharmacist or work in a material science lab or trying to figure out dosage if you're in the medical field. There's all kinds of uses that we can put to stoichiometry to, right? So chemists need to be able to make predictions about the amount of products produced in a chemical reaction. So again, let's say you're trying to make some aspirin, right? You'd like to know how much of the acetylsalicylic acid, which is the active ingredient in aspirin, is going to be produced, right? You might, right, be involved in mining, right? And you might want to extract some precious metals using chemical reactions. But you'd want to know how much you can extract and how much you might be able to precipitate out. In terms of like cost-benefit analysis, right? It's important to be able to make these predictions, right? Or let's say someday you get stuck on Mars, right? And maybe you're trying to figure out how much hydrogen to ignite and react with oxygen to produce water so you can grow potatoes, right? Also, having strong stoichiometry is going to come in handy if you want to avoid a giant explosion. You guys get the idea. We need to be able to make prediction about how much of something we will produce in a reaction when we know how much we're starting with, right? And the law of conservation of mass and what you guys should have already learned about moles, right, will tie this all together, right? So we're going to calculate that amount. Now, you have to be a good measurer and a good lab technician to actually get that exact amount. But we're calculating how much we would expect to get. Okay? Now, that's being said, what do we do to make stoichiometry work, right? So let's consider the combustion of propane. All right? So we're going to go back to our balanced chemical reaction. So in this case, we have propane, C3H8, in reaction with oxygen. So it's a typical combustion reaction. And we're going to assume full combustion in which we produce carbon dioxide and water. Now, last unit, you guys learned how to balance a reaction, right? By adding these little coefficients in there to make sure we have the same amount of hydrogen, the same amount of carbon, the same amount of oxygen on both sides of the reaction. We end what we start, the same amount that we started with. It's just been moved around and transformed, if you will, right? The total amount is there, okay? So the coefficients mean that we have a certain number, right, or a ratio, right, of one compound or element to another, right? So in this case, right, we could read this as, 1 mole of propane, no coefficient there, so we assume that's 1, right, will react with 5 moles of oxygen gas to produce 3 moles of carbon dioxide and 4 moles of water. All right? Now remember, a mole of something is referring to how we turn that atomic mass unit into grams, right? It's referring to a whole bunch of particles. But it's a mole ratio in our practical sense in terms of laboratory experiments. You could say 1 molecule of propane reacts with 5 molecules of oxygen gas, right? But that wouldn't be giving us a measurable quantity. So we'll refer to it in terms of moles. So it's a ratio. 1 mole of propane to 5 moles of oxygen, right? Will produce 3 moles of carbon dioxide and 4 moles of water. All right? Now, when you go into the laboratory, though, you don't just have a balance that measures in moles. You're going to have a balance that measures in grams, which is why I taught you how, right, to convert grams into moles so that we can combine a mass measurement with a balanced chemical reaction. All right? So we're always going to start with writing a balanced molecular equation first, right? 2, we're then going to convert our known quantity, which is usually going to be in grams, to moles. And you should have learned how to do that in the last lesson. 3, you're going to multiply by the mole ratio expressed in the balanced molecular equation. And then 4, you convert to whatever unit you want. Again, it's typically going to be grams. So if I start with 60 grams of propane, how many grams of carbon dioxide will be produced when that propane reacts with oxygen, right? Or we might do liters, right? Sometimes you might be asked to express that in terms of like molecules or atoms, but that's not really a practical thing that we need to know. Okay? Now, let's see what this looks like in practice. So you guys are going to be doing this in kind of pencil paper form because, well, eventually you might get to a lab in it. But so let's say, for example, I know that I'm beginning this reaction with 59.4 grams of propane gas, right? So if that's my starting quantity, this is my reactant, carbon dioxide is one of my products, how much carbon dioxide am I going to end up with, right? Well, step 1, right, we need to have that balanced molecular equation, which I just showed you on the last slide, so we'll pull that back up, right? Because we need to know ratios, 1 to 5 to 3 to 4, right? But in this case, I'm concerned about the ratio of propane and carbon dioxide, right? I could, if I wanted to, also figure out oxygen, gas, and water, but in this case, the question's asking you how much CO2 will we produce if we combust 59.4 grams of propane gas. All right? Now, the next step then, whoops, excuse me, getting ahead of myself. And technical issues. All right, we're going to be ready to move on though. So, we've got our balanced molecular equation, right? We have our known quantity, which is 59.4 grams of propane gas. We're going to convert that quantity to moles, right? And you should have learned in the last lesson, if you want to go from grams to moles, you need to divide by the molar mass. All right? So what we're going to do is we're going to figure out the molar mass of propane gas, right? So I've got 3 carbons and 8 hydrogens, right? So I'm just taking the number of hydrogens times the mass of hydrogen and the number of carbons times the mass of carbon. And when I add those quantities together, I should get 44.11 grams per mole, okay, for propane. Okay, now I need to convert this quantity. I don't have 44.11 grams. I don't have exactly 1 mole. I have a little bit more than 1 mole. So all I'm going to do is, for step 2 here, I'm going to go 59.4 grams C3H8, right, and multiply that by 1 mole over 44.11 grams, right? And that is going to give me a quantity of 1.5 moles of propane, right? Now, I did that a little bit fast because how to convert to moles was last lesson, right? So make sure you go back to the intro to moles if you don't understand what I just did right there. Okay? Now, step 3, I'm going to multiply by the mole ratio. Right? So my mole ratio, again, I'm trying to compare propane gas to carbon dioxide. So I am worried about this 1-to-3 ratio. Right? I'm not worried about oxygen and water. They are a part of that reaction, but that's not part of my calculation in this case. Right? So, I have 1.35 moles of propane. Step 3, I'm going to multiply my 1.35 moles of propane by my ratio of 3 to 1. I'm going to write it as 3 moles CO2 over 1 mole C3H8. All right. Now, I'm going to cancel out my moles of propane. So I'm going to go 1.35 times 3, and that should give me a quantity of 4.04 moles of carbon dioxide. Okay. Now, so what I've done here is I've put these into like terms, right? So that's why we have to use moles. We can't just multiply the mass by 3 because the molar mass of CO2 is not the same as the molar mass of protein. We have to first convert the number to moles. So we did that here, right? Then we multiply by the mole ratio. That's step 3. The last thing I'm going to do is convert to my desired unit, which again is grams. So this is in moles at the moment, right? So in my final step here, I'm going to go moles to grams, which means I need to multiply and this is not liking me, multiply by the molar mass. All right, so I'm going to go 4.04 moles of CO2, right, times the molar mass of CO2, which is 12.01 plus 2 times 16.00, which should be 44.01. So I'm going to multiply that by 44.01 grams per mole. And I should get a final quantity of 178 grams CO2. All right? So that is the way this looks in practice. I know that's just one example, but you guys ought to be able to jump on that ChemQuest and get lots of extra practice, right? If you would like some help with this, in a normal year, we'll be doing that in class. If you happen to be watching this in a COVID year, like when I'm making this video, that would have to be done through like a Google Meet or something. All right, but get after it. This is good, solid chemistry right here.